All right, let's talk about alternating currents. It's this invisible force that's buzzing all around us, powering pretty much everything we rely on every single day. I mean, from the lights above your head to the very device you're using to watch this. It's everywhere.
So, to really get a grip on this, we've got to start with the two main types of electricity. On the one hand, you've got direct current, or DC. Think of it like a river, just flowing steadily in one direction. That's what you get from a battery. But on the other hand, we've got alternating current, AC. This one's more like the tide, constantly ebbing and flowing, switching its direction back and forth. You can see it right there in that classic wave shape.
So wait a minute. If alternating current is just electrons, well, wiggling back and forth without really going anywhere, how on earth does it manage to do any actual work? How does it power your TV or toast your bread? It sounds a little weird, right? Almost like a paradox. But don't worry, stick with me and I promise by the end of this, it'll all make perfect sense.
Okay, here's our game plan. We'll start by comparing AC and DC. Then we'll get into how to describe the AC wave. After that, we'll look at how to read these waves with a tool called an oscilloscope, figure out where the real power of AC comes from, and then we'll solve a few problems. And finally, it's your turn.
All right, first up, AC versus DC. Let's really get into the core difference in how those electrons are moving.
Okay, so here's the key difference you need to remember. With DC, from something like a battery, the electrons are on a one-way trip. They literally travel from one end of the wire to the other. But with AC, which is what's coming out of your wall sockets, the electrons barely move at all. They just jiggle back and forth in their spot, passing energy down the line to the next electron, kind of like a human chain passing buckets of water to put out a fire. The water gets there, but the people stay put. That's AC.
Okay, so we've got this back and forth motion. How do we actually describe it? Well, that's where the language of math comes in. This repeating pattern you see with AC is called a sinusoidal wave. And here's the really cool part. Its shape is exactly the same as the motion you'd see in something like a swinging pendulum. That's what physicists call simple harmonic motion. And because we already have the math to describe that, we can just borrow it to talk about AC. Super convenient. Now, to really describe any AC wave, you only need to know three things. First is the peak value, which we write as V0 or I0. That's just how high the wave gets, its maximum voltage or current. Then there's the period, or T, which is simply the time it takes for one complete cycle, one full back and forth. And finally, the frequency, F. That's how many of those cycles happen every second. For example, the power in your house is probably running at 50 or 60 hertz. That means the current is flipping its direction 50 or 60 times every single second. Wow. And of course, we can wrap all of that up into these neat little equations. These formulas let you find the exact voltage or current at any specific moment in time. You can see our peak value, V0, right there at the front. And that squiggly W symbol, that's omega, the angular frequency. All it is really is 2 times pi times the regular frequency. It's just a handy way to connect the back and forth motion of the wave to the math of a spinning circle.
Okay, let's put this to the test with a quick example. Imagine you see an equation like this. V of t equals 24 sine of 380t. All we have to do is compare it to our standard formula. The number out front, that's our peak voltage, V0. So super easy, it's 24 volts. And the number next to the t inside the sine function? That's our angular frequency, omega, which is 380. To get the real-world frequency, f, we just do omega divided by 2 pi. So 380 divided by 2 pi, and that gives us about 60.5 hertz. See? Not so bad.
So all this math is great, but electricity is invisible, right? So how can we actually see these waves? Well, we use this amazing piece of kit called a cathode-ray oscilloscope. A cathode-ray oscilloscope, or CRO for short, basically just draws a picture of the voltage for us. It plots the voltage on the up and down axis and time on the left to right axis. And that grid pattern you see on the screen, that's not just for looks, it's a ruler that lets us take really precise measurements of the wave.
And measuring the frequency with a CRO is actually a really straightforward 4-step recipe. Step 1, look at the screen and count how many horizontal grid squares it takes for the wave to make one full cycle. Step 2, check the time-based knob on the machine. It tells you how many milliseconds each one of those squares is worth. Step 3, multiply those two numbers together. That gives you the period, t. And finally, step 4, just calculate the frequency, which is 1 divided by t. And a super important tip, always remember to convert milliseconds into seconds before you do that last step.
Let's try it out. So in this scenario, the time base is set to half a millisecond per centimeter, and we can see that 2 full cycles fit into 6 centimeters on the screen. Okay, so if 2 cycles are 6 centimeters, that means 1 cycle must be 3 centimeters long. Now we just multiply that 3 centimeters by our time base of 0.5 milliseconds per centimeter. That gives us a period of 1.5 milliseconds. Convert that to seconds, calculate 1 divided by that number, and voila, we get a frequency of about 667 hertz.
Finding the peak voltage is just as simple, but this time we're looking at the vertical direction. First, you check the setting for the vertical scale, the Y gain. Here, it's 5 millivolts for every centimeter. Then, you measure the amplitude, and that's key. You measure from the center line up to the highest peak. In this case, that's 1.4 centimeters. So, you just multiply them. 1.4 centimeters times 5 millivolts per centimeter gives us a peak voltage of exactly 7.0 millivolts. Easy as that.
Okay, so this brings us right back to that big question from the beginning. How does this back and forth current actually deliver power? Well, the answer has a name, root mean square, or, as we usually call it, RMS.
Now here's the real puzzle. If you just take a simple average of an AC wave over one cycle, you get 0, right? The positive part completely cancels out the negative part. But that can't be right because we know our appliances work. The light bulb still lights up. So just averaging it in the normal way is clearly not the right way to think about the power.
The secret is hiding in the power formula, P equals I squared times R. The key here is that little squared symbol. When you square a number, it doesn't matter if it's positive or negative, the result is always positive. So even when the current is flowing backwards in the negative part of the cycle, the power being delivered is still positive. It means the heater is heating up on both the forward and the backward push of the electrons. So the power pulses, but it never goes negative, and the average is definitely not 0.
So to make life easier, and to compare AC to DC in a meaningful way, we use a special kind of average called the root mean square, or RMS value. Here's the best way to think about it. The RMS value of an AC voltage is the DC voltage that would give you the same amount of power. It's the equivalent. So a 12-volt RMS AC source will light up a bulb just as brightly as a steady 12-volt DC battery. It's the effective value. And you know what? The map to find it is super simple. The RMS value is just the peak value divided by the square root of 2. That's it. It works out to be about 70.7% of the peak. And here's a fun fact. When the electricity supply to your home is listed as, say, 230 volts, that's the RMS value. The actual peak voltage is way higher. It's jumping all the way up to about 325 volts during each cycle.
All right, we've got all the pieces of the puzzle now. We understand the equations, peak values, and his super useful RMS concept. So let's put it all together and solve a real-world problem.
Okay, check this out. A common 1.5 kilowatt heater plugged into a 230 volt RMS supply. How do we figure out the peak current and its resistance? It's a 3-step process. First, let's find the RMS current. We know power is voltage times current, so current is just power divided by voltage. 1,500 watts divided by 230 volts gives us an RMS current of about 6.52 amps. Step 2. Find the peak current. We just take that RMS value and multiply it by the square root of 2. And look at that, the peak current is actually 9.23 amps. That's a pretty big surge happening 50 or 60 times a second. Finally, step 3, the resistance. We can just use good old Ohm's law with our RMS values. Resistance is voltage divided by current. So 230 volts divided by 6.52 amps gives us a resistance of about 35.3 ohms. Done.
Okay, time to wrap things up. Let's put your understanding to the test with a few final questions and some essential tips for when you're doing this on your own.
Let's do a quick fire round. Ready? Number 1.
If V equals 18 sine 500t, what's the peak voltage and frequency? Well, V0 is 18 volts, and the frequency is 500 over 2 pi, about 79.6 hertz. Got it? Okay, number 2, a CRO problem. One cycle is 4.5 centimeters. Time base is 0.2 milliseconds per centimeter. What's the frequency? Well, the period is 4.5 times 0.2, which is 0.9 milliseconds. That gives a frequency of about 1.11 kilohertz. And last one, amplitude is 2.2 centimeters, Y gain is 2.0 volts per centimeter. The peak voltage, it's just 2.2 times 2.0, so 4.4 volts. And remember those crucial tips. Always convert milliseconds to seconds. Measure from the center to the peak for voltage, and keep your answers to a reasonable number of significant figures.
So let's end with this one last thought, which really gets to the heart of it all. What is the big deal about the RMS value? Why is it so important? Well, it's because it's the magic translator. It lets us take the wacky, oscillating world of alternating current and talk about it using the simple, steady rules of direct current. It's the number that tells you what the real, effective power is. It's what lets us use our trusted old formulas like V equals IR on a current that's constantly changing. In short, the RMS value is what makes AC understandable, predictable, and incredibly useful. It's the key that unlocks it all.